Good afternoon, everyone. We're about to start. My name is Vesdelina Stanko, and I'm the director and the founder of the Berkeley Math Circle. This was the 25th or 6th year. I keep forgetting. Well, one of the two. 25th, Alan says, okay, 25th year. And today we have a very special person, one of us. Espen Sletnes will be giving the BMC Colloquium. I'm going to read the official bio, and then I'm going to tell you things that are not in this bio about Espen. So Espen, you can close your ears for the last part. Not eyes, ears. So Espen joined the Berkeley Math Circle, how many years? 11 years ago, that's right. Spring 2012. He, I believe, was then in the elementary level of the Math Circle. And in more recent years, he has served as an instructor for the advanced group, as a grader, problem writer, and coordinator for the proof-based monthly contest. And we have some awards to give today. Espen earned the Gold Award last year at the USA Math Olympiad and attended the National MOP, Mathematical Olympiad program, which is the training program of the US team for the International Math Olympiad. Espen is a published math researcher who began his research journey in 6th grade. The following year, he started interning at the MIT Primes USA research program for several years, completing various individual and group projects in combinatorics. He received the Spirit of Ramanujan Fellowship 3 times in 2018, 19, and 2020. His work has been recognized by the Broadcast Masters National Science Fair, the Shintan Yao High School Science Award, Davidson Fellows, the Mathematical Association of America Outstanding Presentation Award at the Joint Math Meetings, and others. In recognition of his achievements, Minor Planet 34379, discovered by MIT Lincoln Laboratory in 2000, was named Sletnes in his honor. And a few words from me. The first time I was made aware of Espen was in the beginners group of BMC. This was probably the time when we just started splitting the groups. There was only beginners and advanced. I forget what it was at that time, but maybe only 2 groups. And Espen was in the beginners group, which started in 5th grade, but he was only in 2nd grade. He was advanced there from the BMC elementary instructors who said, Zvezda, we can't keep him here anymore. Take him after 1 or 2 years there. And in the next few years, he quickly advanced to the advanced group of the Berkeley Math Circle. We had to disqualify him from the monthly contests. This sounds really horrible when I say it in the beginning, but he was just basically winning them, and no one else had a chance, no matter how many times we handicapped him. Instead, he became one of the graders, the coordinators, and eventually one of the problem composers for the contest. In 6th grade, Espen took my class. It's called Math 110 in linear algebra. This is an upper division class of about maybe 400 students, most of them math majors. So he was in 6th grade, and I have lots of interesting stories to say. His GSI too, and his peers. Suffices to say that, to my memory, Espen finished first the final exam and attempted to leave, but I don't think his parents were there or something, so I told him, Espen, you have to wait just a little bit, so you have a ride home or whatever was happening, but basically he was prevented from leaving way too early. It was a perfect score. So that was just the beginning. For many people, that would be beyond the end, but for Espen in 6th grade, he was only beginning his math career here at Berkeley. And he went on to take a bunch of graduate courses, not just in math, but in other disciplines on campus. And after his talk, you guys will have the opportunity to ask questions about where he's going and other things in addition to the math. So let us all welcome Espen Sletnes.
Okay, hello. As was just mentioned, I got into math pretty early on, but in high school, my focus in math took a quite sharp turn. I got into Olympiad mathematics, and in Olympiad math, the appeal of the problems is that they really test your problem-solving abilities. In Olympiad math, the problems are meant to be solved using somewhat elementary techniques that any high schooler could have access to, but the problems are designed to be very ingenious so that the solutions to them, you have to be really aware of how you're approaching the problem, what problem-solving techniques you can use in order to try to attack the problem and make it solvable. So as you go through Olympiad math, as you work on more and more problems, you sort of develop a repertoire. You see what types of patterns appear in problems. You get a sense of what a problem will look like, even after just reading it. You'll build an intuition for what problem-solving techniques you might need to use in any particular problem. But then there are some problems that just defy your sense of intuition, that they look like they should be solvable using some methods, but they really just aren't. They look like problems that should be solved in way X, but instead they bring you through a journey, an entire proof that seems to come out of nowhere. And I think of these problems as quite magical. And so today, this is a homage to these problems. I'm going to be going through some of the most magical problems I've ever encountered, some of the problems whose solutions just defy all expectations. So we're going to begin with the Graham-Pollack theorem. It was developed in 1971 or something, and it was originally a question about telephone circuit boards, designing telephone circuit boards to connect people. And the statement of it looks like this, and that's a lot of words. There's complete graph, there's complete bipartite graphs, there's partition. We're going to look at a much more approachable statement, which is as such. You have 101 players. 101 players competing in several rounds of a game. And each round of the game will have 2 teams selected from the players to compete against each other. You have 101 players, they're going to play rounds of a game. In the game, you take one group of players from them and another group of players from them. You don't have to use all the players at once. And then you have these 2 teams face off against each other. Now, given that every player faces off every other player exactly once, for any pair of people, they will be in opposing teams in exactly one round of the game. Show that there are at least 100 rounds. That's the problem statement. Prove that it takes at least 100 rounds to orchestrate the players in such a way such that every 2 players will face off against each other exactly once. So, it turns out that you can't do it in exactly 100 rounds. The one such way is you line all the players up from tallest to shortest, and you have the tallest player be on a team by themselves facing against the 100 other players. And then they'll face off against everyone. Then you move on to the second tallest player, who's already faced off against the tallest player, but then you put them on a team facing against everyone else. And then you move on to the third player and you do the same thing. Everyone will face off against everyone shorter than them in a round. And everyone will also face off against someone taller than them who had a round devoted to themselves before. You only need 100 rounds because when you get to the shortest player, they don't need to face off against anyone else. So only all 100 other players need to face off. So it is possible to do this in 100 rounds. And we are going to see why you can't do it in less. So here's the idea. Here's where the magic of the problem comes in. If we have two teams, A, B, and C, and X, Y, Z, these are just example variables, they can be any size. But if you have two teams of players consisting of players A, B, and C facing off against players X, Y, and Z, if we want to understand which players face off against each other in this matchup, what we can do is instead of thinking of this as a combinatorics problem, we think of this as an algebra problem. What we're going to do is we're going to represent A, B, and C facing off against X, Y, and Z as this expression. If we have the team A, B, and C, we're going to write A plus B plus C, and then multiply that by X plus Y plus Z. And you'll notice that in this expansion, every pair of players that face off against each other is included once. If you have players B and Y on opposite teams, there will be a term for them when you expand this product out. What happens when you multiply these expressions is that every two variables corresponding to players on other teams, on opposite teams, will be included in this sum. And so we must have that if each player faces against each other player exactly once, then if we do this expression for every round, if we take the sum of one team times the sum of the other, what we are going to achieve is when we add up all these expressions across all rounds, every two players, since they face off against each other exactly once, should appear once in the final sum over all rounds. If we create the variables x1 through x100 for all the players, then these terms, sum of one team times sum of another team, must sum to the sum of the products of every pair of players by the problem conditions. So, now that we turn this into an algebra problem, we can examine this term. The sum for all players, the sum for all I less than j of xi times xj, well, this is just half of this sum, where instead of saying I less than j, we can just say I is not equal to j. And this will count every pair twice. Instead of counting players 3 and 5 exactly once, you only have to compare players 3 and 5 and players 5 and 3. And so this will get you that this sum is one half of this sum. But now, the sum over all I not equal to j of xi xj, well, this is just the sum over all I and j between 1 and 100 of xi xj minus the sum of when they're equal, right? By complementary counting. And so this product right here, you'll just notice is the expansion of the sum of all xi squared. When you take the sum of every player and multiply it by itself, when you expand that out using FOIL, every two players will face off against each other in that expansion. And then we're subtracting off when I equals j, so we're just subtracting off xi squared. And of course we have to keep the 1/2, so we're dividing by 2. So this expression equals this. And again, this represented the players that face off against each other. So this right here, this is the interactions if we sum over teams. The set of players that face off against each other in the rounds should be every pair of players. And so that's how we get this equality. And so we have this equation. What do we do with it? Well, here's the second key idea of the problem. Now that we turned it into an algebra problem, we have an equation we can work with. What we do is we're going to try to make this equation false. We're going to try to plug in values for the variables. We're going to try to choose values for x1, x2, and so on in order to make this equation false. We're going to make it work hard to remain true. And in particular, we're going to make it work so hard we need at least 100 rounds. That's the idea. We're going to impose and we're going to make this equality have to satisfy so many restrictions. It needs many rounds in order to be able to satisfy them all. Okay, so here's how. We're going to select values of x1 through x100 that satisfy a specific system of linear equations that we're going to engineer specifically for this equation. What we are going to do is we're going to try to make this left-hand side positive, while this right-hand side is negative. And a positive number can't equal a negative number. That's how we're going to try to falsify this. So to make the left-hand side positive, one example of positive numbers, or at least non-negative numbers, are squares. Perfect squares are always non-negative. When you multiply a positive number by itself, it's positive. Negative by negative, it's still positive. 0 by 0, that's the only case in which it's 0. So we're going to make every term on this left-hand side a square. How we do this is we're going to pick variables. We're going to pick variables such that the sum of every team is the sum of the team they're facing against. And so every term in this product becomes a perfect square because these two terms are equal. So this left-hand side is now non-negative. Now for the right-hand side, well, notice that we're subtracting a lot of squares. Squares, again, are positive. So if we're subtracting a lot of squares, we already have quite a lot of negative terms. The only problem is that we have one single positive square. And so we're going to set that to just be 0. We're going to set the sum of all players to be equal to 0, so that the right-hand side is less than or equal to 0. So now we have some rules on how we're going to choose x1 through x100. Now note that this system of linear equations, if we set the sum of every team to be equal and we set the sum of every player to be equal to 0, note that this does have indeed one solution. This system of linear equations has the solution, every variable being 0. If every player is 0, the sum of any team is 0. So any team equals any other team. Likewise, the sum of all players is equal to 0. So there is a system to these linear equations, but I claim that it has to be unique. And here's why. If this left-hand side is 0, and this square is 0, what we have just forced is that this final thing in the equation is also 0, in order for the equation to be true. So if the sum of the squares of all variables is equal to 0, then every variable must be 0. Why? Well, if any variable were positive, then the entire sum would be positive. If I had a sum of squares, and if any of these squares are positive, then because the rest are non-negative, adding all of these variables gives an at least as large number. So if this is equal to 0, then all variables are equal to 0. So what we have just shown is that any set of variables which satisfy these linear equations right here, if variables satisfy these linear equations, they must all be 0. And now we're done. Here's why we're done. Because there are 101 variables. There are 101 variables, and we know that the system of equations has exactly one solution. Well, if a system of equations has exactly one unique solution, there must be at least as many equations as variables. So there must be at least 101 equations. But how many equations are there? Well, there's one for every round, and there's this extra one. So if the number of rounds plus 1 is the number of equations, which is at least 101, the number of rounds must be at least 100. So that was the proof. I find it quite remarkable. It's a combinatorics problem. It is phrased as players facing off against each other in teams. It sounds like a word problem. It's about a game. But the approach to the problem is to represent mathematically what it means for two teams to face off against each other. Mathematically, what it does is you're summing a team and multiplying it by another team. And somehow this algebraic expression faces players off against each other perfectly. And through that, we turn it into a system of linear equations. We turn it into this equation, which we then use as a system of linear equations to try to restrict. We try to restrict this side to be positive and this side to be negative. And by forcing the equation to work to be true, we show that it has to have at least 100 rounds. So if you're lost or you're not paying attention, come back in now. We're moving on to another problem, problem 2. And this is from the 2016 Brazil Olympic event. So what that is when you get to Math Olympiads, like the highest level of Math Olympiads is the International Math Olympiad. And in the International Math Olympiad, 6 people from every country will be sent to the IMO to compete in a series of problems over several days. Now, how they select the team is they take the top performers on national Olympiads, and they're going to bring them to a camp, and the coaches are going to coach these people and train them, and then the top people from the camps go to the IMO. In Brazil's camp in particular, they have this tradition where after contestants have been subjected to the coaches' prompts for however long the camp is, they write a contest called the Brazil Olympic Revenge, where instead of the coaches giving prompts to the students write a contest that they give to the coaches and force them to do their most troll problems that they've written. Anyway, it's a 5-prong contest every year, and so we're going to be doing prompt 5, the hardest problem of 2016 from the Brazil Olympic Revenge, a revenge contest written by the students. And here's what it looks like. Let T be the set of sequences of integers. So T can contain the Fibonacci sequence, it can contain the digits of pi, it contains every infinite sequence of integers you so desire. T is the set of sequences of integers, and there's a function from T to Z. What that means is there's some system where whenever you tell me a sequence, I will tell you one single integer that represents the whole thing. Okay? Every time you give me a sequence of integers, I'm going to tell you one integer back. And suppose that this function satisfies these properties. 1, it is additive. Now what does that mean? It means that the sum of any 2 sequences, when you enter a plus b into the function, you get f of a plus f of b. Well, what's the sum of 2 sequences? When you have 2 sequences of integers, 2 infinite sequences of integers, what you do to sum them is you take the first terms and you sum them. And then you take the second 2 terms and you sum them. And you take the third terms and you sum them. And so you just sum all the sequences of integers, all the corresponding terms in the sequences together. Okay? So that's part of the setup of the problem. We're going to have that for any 2 sequences in the set of sequences of integers. When you input a plus b into the function, you're going to get f of a plus f of b. If one sequence gives you 1 and another sequence gives you 2, then inputting the sum of the sequences gives you 3. The second property is that whenever you have a sequence which is mostly zeros, in fact, it is infinitely many zeros, almost every single term in the sequence is 0, except for one single 1. Whenever you have a sequence like that is basically all zeros, but with one glitch, it will map to 0. So you're given that it's additive, you're given that a few specific sequences, well, I shouldn't say a few, infinitely many, but you're given that some of specific sequences map to 0. The question is to prove that all sequences map to 0. So, those of you who have seen maps before, in the context of linear algebra, group theory, or whatever, might recognize that the first observation to make here is that f of 0 is 0. Bolded 0 here means the 0 sequence, not just one 0, but 0, 0, 0, 0, 0 forever. So f of 0, well, the 0 sequence is also the 0 sequence plus the 0 sequence. So f of 0 is f of 0 plus f of 0, because 0 plus 0 is 0, and that happens in every term of the sequence. So f of 0 equals f of 0 plus 0, and that equals f of 0 plus f of 0. So f of 0 equals 2f of 0, so 0 maps to 0. So that's the first observation. The second that we're going to make is that subtraction is possible. And the trick to subtraction is pretty clever. When we take f of a minus b, and when you subtract the sequences, take the first sequence minus the second sequence, every term of the first minus every term of the second, and you put that in a sequence. So f of a minus f of b, the trick here is to add f of b and then subtract f of b again. If we add f of b and subtract f of b, this is constant because we're just adding something and subtracting it. That's adding 0. But then you know that f of a minus b plus f of b, well, the sequence a minus b plus b is equal to a. And so f of a minus b plus f of b is just equal to f of a by this property right here. So therefore, f of a minus b equals f of a minus b plus f of b, which is f of a minus f of b. And so that's just f of a minus f of b. Okay. Now let's use this property right here. Actually, sorry, we don't do that yet. Right, sorry. Before doing that, note that these two properties give us something else. Say I have the sequence A, and I want to look at a multiple of the sequence. What do I mean by a multiple? Well, if I have a sequence, and I multiply every term in it by 2, that would be the entire sequence times 2. If I, in general, have a number n, what I mean when I say n times the sequence is n times every single term of the sequence individually. We're operating on the whole sequence at once. So, when I have the sequence A, well then f of 2a, what the function does to 2a is just twice what the function does to a by additivity. But then f of 3a is just 3a is just 2a plus an extra a. So f of 3a then maps to 3f of a. F of 4a, well 4a is just 3a plus a. So we can just keep on inducting up. And therefore, f of na should always be equal to nf of a for any positive integer n. For negative integers, we're going to do this process in reverse. We're going to start from 0. And we can subtract it to get that f of negative a is equal to negative f of a. We can subtract a again. We can keep on subtracting a. So in general, for any integer c, multiplying the sequence by c will bring us to c times f of a. So these are the key properties initially. Now, note that these ei, you might think, if you're familiar with the term basis vectors, they sort of act as the basis vectors of T. Otherwise, what you will note is that every sequence is actually a sum of multiples of ei, multiples in this sense, in terms of multiplying a sequence by an integer. And here's what I mean. If I have a sequence like 3, 1, 4, 1, 5, the digits of pi, then I can express this sequence as this sequence plus this sequence and so on. You'll know that this is a sequence with almost all zeros, except for 1, 1, then multiplied by 3. That's what goes on here. E1 is the sequence of all zeros except for 1, 1, and then what we're doing is we're just having E1 3 times. So, if we add 3 to the first digit, then we add 1 here, then we add 4 here, then we add 1 in the fourth digit, and so on. If we just keep on summing these, 3, 1, 4, 1, 5 goes to 0 plus 0 plus 0 plus 0 plus 0, and so on. And so this should equal 0, right? Well, it turns out that there's a flaw in this argument. There's a key flaw. Suppose I look at that chair and I say, well, if I walk half of the way to the chair, I will still not be touching the chair. And this is true. And then if I walk half of the way to the chair again, well, this is still true. This is Zeno's paradox. And if I just keep on walking half of the way, I will never actually touch the chair. But there's a little problem with infinity. It is true no matter how many times I do it. If I did this 100 times, 1,000 times, it would still be true. But the problem is, it would not be true if I did it infinitely many times. If I keep on walking towards the chair, there's a very, very real possibility that I'll crash into it. And this is the problem with this argument. Another example is that if we take the floor of a number like 0.9, this is 0. We can ignore the digits after the decimal point. We can ignore 2 digits after the decimal point when taking the floor. That's still 0, and so on. But we cannot actually ignore all the digits of 0.9 and 9, because 0.9 and 9 is actually 1. So, floor of 0.9 and 9 forever is 1, and so this is the flaw. The problem with this is that sure, this property allows us to add a sequence to itself once or twice or 3 times. And in fact, if we can do it n times, we can do it n plus 1 times. So we can induct forever, but we cannot induct to infinity. Forever does not reach infinity. That is the issue. We cannot actually use this argument because it involves saying that an infinite sum would work in f, and we can only prove that finite sums would work in f. So we only can actually do this if only finitely many EI are used. In other words, we only have now shown that if a sequence has all terms being 0, except for a finite number of them, only then are we done, because only then can we use EI to build up the sequence we want. So f of any sequence with all terms being 0, except for a finite number, would be 0. But that still doesn't leave that still doesn't cover most of the sequences. Most of the sequences in our function, right, most of the sequences in T have a lot of non-zero terms. Most of the sequences have infinitely many non-zero terms. So we're very not done. So the key insight in this problem is actually not about a trick you have to use. It's about the mindset. You see, when you're doing this problem, you generally try to think, oh, I want to show that all x map to 0. And this is actually the wrong way to approach it. The way that actually begins to make progress is instead of looking to show that any x maps to 0, we just want to find x that maps to 0. What we're going to do is we're going to build our knowledge about x from the ground up. We're going to find more and more values of x which map to 0 until we found that everything maps to 0. That's the idea. So let's just find another sequence that maps to 0. We already know that any sequence with mostly 0 terms, with all but a finite number of terms being 0, maps to 0. So what other sequences can we try? Well, it turns out that the first one that gives you anything is the powers of 2. Here's what happens. Say I have f of the powers of 2. Say I look at the powers of 2 as a whole, and I try to evaluate f at these values, or at the sequence. Well, what we just argued was that a finite number of terms do not matter. But we just argued that if a finite number of terms in the sequence are non-zero, it's the sum of EI, and we can add that to any sequence. In other words, any finite number of these digits does not matter because we can mess around with them by adding EI. And as long as we add EI only a finite number of times, we're okay by our induction from earlier. And so, in this sequence, we're going to just do one thing. We're going to change that 1 to a 0. And now, we have a sequence of even integers. Every term of this sequence is even because all of them are powers of 2, and the only odd power of 2 is 1. So now it's 0. Now every term is even, and so we can divide by 2. Because this sequence is this sequence times 2, from the scaling property earlier, f is now 2 times the number. So f evaluated at the powers of 2 is even. F is 2 times f, a different value of f. But this different value of f looks awfully similar. In fact, this different value of f is also even, because we can change that 1 to a 0, and we can divide by 2 again to get 4 times this. Or 8 times this, where we change this 1 to a 0 again. And so, not only is this value of f even, but it's divisible by 2, it's divisible by 4, it's divisible by 8, it's divisible by every power of 2. And here's the thing, it's an integer, right? It's not a real number that we can divide by 2 a ton of times. If we have a number like 1,000,000, and we divide it by 2 too many times, it's eventually going to be too small. It's going to be like 1,000,000 over, for example, 10 to the 20 would be less than 1. It would be between 2 integers. The problem with it being divisible by too many powers of 2 is that you just cannot keep dividing integers by powers of 2. They have only finitely many 2's in their prime factorization, except for the one number which doesn't have a prime factorization, and that would be 0. This value of f, in order to be divided by 2 as many times as you would so desire, it would have to be equal to 0. F of the powers of 2 is equal to 0. So that's the first key point in the argument. Now, note that this doesn't really require powers of 2. The entire thing we're making use of here is that we can keep on dividing. So, all I actually really require of a sequence for it to be mapping to 0 is that if I get rid of as many terms as I so desire, I can get the GCD to be as large as I want. The GCD of all numbers. If I all that I'm requiring of the sequence is that if I remove finitely many terms, because again, we don't care about finitely many terms, we can add PIs. If I remove as many terms as I so desire, the sequence should have larger and larger GCD, so that I can keep on saying, oh, f is divisible by a larger and larger number, so it must be 0. For example, the factorial numbers would work. If I had the sequence 1 factorial, 2 factorial, 3 factorial, and so on, and I removed, say, like 1, 2, 3 factorial, then the remaining terms would all be divisible by 4 factorial. Because 4 factorial divides n factorial for any n greater than 4. So, all I'm asking of the sequence is that it has increasing GCD. Now, this is still not nearly all the sequences, but it is quite powerful. We have a lot more knowledge about sequences that map to 0 than we did before. In fact, I claim that it's super powerful. I claim that this actually gets us to all values of x. And here's how. We're going to represent any general sequence x, like x1, x2, x3, and so on. We're going to write it by using 2 sequences with increasing GCD. We're going to be using the powers of 2 and the powers of 3. We're going to utilize them to represent every sequence as a sum. And then this property will make a sum. So here's how. Because any power of 2 and any power of 3 are relatively prime, they share no prime factors. By Bézout's lemma, or the Euclidean algorithm, or whatever you want to call it, any integer can be expressed in this form for 2 integers. They can be expressed as a multiple of a power of 2 plus a multiple of a power of 3. Because the power of 2 and the power of 3 have GCD 1. But then, f of x, f of any sequence, must then, if we write it out, it must be equal to this expression. And we're representing every single term of f by a sum of a larger and larger power of 2 and a sum of a larger and larger power of 3 times constants. But now, because this is a sum of sequences, we can split it up by this property into f of this sequence and f of this sequence. F of some constants times the powers of 2, and f of some constants times the powers of 3. And we know that the sequence has increasing GCD. If I delete 2 terms, the remaining terms are divisible by 2 cubed. If I delete 2 terms here, the remaining terms are divisible by 3 cubed. The more terms I delete, the larger the GCD will get. And so 0 plus 0, because these have increasing GCD, they are both mapping to 0. And 0 plus 0 is 0. So we're done. We've managed to represent every single sequence as a sum of sequences which map to 0. So while the first problem was a combinatorics problem turned into an algebra problem, I like to think this is an algebra problem that was turned into number theory. Somehow, the key to killing this problem was, rather than trying to show that sequences map to 0, which is how you would do it if you're treating it as an algebra problem, what we did is we found sequences with a property that they map to 0, and we just kept on finding more and more, and then turning it into a problem about representing integers, turning it into a number theory problem. And I find that this proof is quite remarkable for that. It's so counterintuitive that you would want to look for explicit sequences. Anyway, that was that problem. Time to do it again. The next problem is pictures. This is a problem from the Elmo. The Elmo, it's a poem I wrote for the Elmo. The Elmo is, well, the last problem was from Brazil, this problem is from America. In our National Math Olympiad camp, the students, again, write problems, but rather than writing them for the coaches, here, the Elmo is a contest that people returning to MOP, which is our national math camp, it's a contest that people returning to MOP write for the new MOPers, to welcome them into camp, if you will. A warm, sometimes not welcome welcome. But we give them problems. The Elmo, by the way, it stands for a different thing every year. Last year, I believe it stood for Olympians Enjoy Mixed Up Letters. This year, it stood for Elmo, Let Me Out. So the Elmo, how it works is we put the new moppers in a room for 4.5 hours for 2 days. So 4.5 hours one day, 4.5 hours another day, 9 hours in total. Each day they're given 3 problems to work on. And so this was the 3rd problem on the first day. It is the hardest problem that they were given on the first day of camp. Or sorry, on the first day of the And here's how it looks. Given 2 uniformly random points on the perimeter of a regular 2022 gun of unit area, that's a lot of words. What's the median value of the distance? Even more words. Okay, so let's parse this. First of all, here's a regular 2022 gun of area 1. For comparison, here's a circle of area 1. I hope you can tell the difference. We have a 2022 gun of area 1, and we're going to pick 2 uniformly random points in it. We can pick a point here, we can pick a point here, wherever we want to choose our points. We're going to pick 2 uniformly random points on the perimeter of it, just on the edges of the 2022 gun. We're going to pick 2 uniformly random points, and we're going to ask, what's the median value of the distance? What does median mean? Well, the distance between 2 random points is a random variable. It's a random distance. And the median value of it is the distance d such that they're at least as close as d half the time. Exactly half the time. The median value is, if the points are a and b, the median value is the number d such that the distance AB is less than d exactly half the time and more than d exactly half the time. It's the number d such that comparing the distance AB to d is the same chance as a coin flip. So we want the median value of their distance. Well, we have a 2022 gun of area 1. A circle is a good approximation. Let's solve it for a circle first. If we have a circle of area 1, well, pi r squared is 1. So the radius is equal to 1 over pi square rooted. So the square root of 1 over pi is equal to the radius of the circle. Now what's the median value of the distance? Well, if I have any point here, on the bottom say, then half of the points, we want to know which half of the points are closer and which half of the points are further. Well, that's just the bottom half of the points, okay? If I have a point here, the bottom half of the points are closer to the point, and the bottom half are further away. Or sorry, and the top half are further away. So the boundary point between bottom half and top half is just the point on the right or left. Now the distance from this point to the bottom point, well, that forms a 45, 45, 90 triangle that I'm highlighting right here. And so the bases are square root of 1 over pi because they're the radii of the circle. And so by the Pythagorean theorem, well, the square of each side length is 1 over pi. So the hypotenuse has square 2 over pi, so the hypotenuse is square root of 2 over pi. So the median value of 2 points on the perimeter of a circle, the median value of their distance is square root of 2 over pi. We want to know what the answer is for the 2022 gun, which looks like the circle, but is slightly off. It is deformed, it is pushed in on the edges and pulled out at the corners. So we want to know the median value. Who thinks it's more than the circle? Raise your hand. Just guess. Hedge your bets right now. I see no one is, okay, maybe a few people. Who thinks it's less? Okay, we shall see who's right. We shall have fun with this. So without further ado, let's get into it. Let's try to find a median value. Now it's really hard to understand the 2022 gun when it's really doing a great job of looking like a circle. So let's fix that. We're going to travel to the year 6. 2016 years ago, they hadn't invented 2022 guns yet. They only had hexagons. And in that year, the Elmo 3 problem in year 6 looked like this. Given 2 uniformly random points on the perimeter of a hexagon with unit area, what's the median value of their distance? Okay, so we have 2 points. Let's call them A and B. 2 uniformly random points. Well, without loss of generality, it doesn't really matter which side of the polygon A is on, so we're going to just assume it's on the bottom side. So
let A be on this blue segment right here.
We want to know the distance such that B is more than that distance away from A exactly half the time.
Well, if B is on the top side, it's always further away than if B is on the bottom side. If B is on the bottom side, it's at most like two edges, at most one edge away from B, because the most extreme is if A and B are on opposite sides of the edge. But if B is on the top side, it must be at least two sides of the hexagon away from A, because the closest they can be is when they're like directly facing each other. So when B is on the top, the distance is always larger than when B is on the bottom. And these have equal chances of occurring. So if we're looking for the median value, if we're looking for the distance such that it's more half the time and less half the time, we really can just ignore the top and bottom side, right? They have an equal chance of being top and bottom, so these cancel out. We can assume that B is on the left two sides or the right two sides. And if we're doing this, we might as well also assume that B is on the left, because left and right are symmetric. So we're going to just assume that B is on the left side of this hexagon. So A is a random point here, and B is a random point here.
We want to know the median value of their distance.
So it's rather hard to deal with two moving points.
We have one point that's following some crazy path, one point that's following only a slightly better path, and looking at the distance between them is just really hard to handle. Both ends of the segment are moving around. That's annoying. So the first key idea of this problem is going to be to handle that. The way we're going to do that is instead of having a hexagon and choosing points in it, we're going to make the points pick the hexagon. What I mean is that we're going to look at the frame of reference of A. We're going to look at this diagram from A's point of view. And in A's point of view, A is completely stationary. It's not a random point on the hexagon. The hexagon is a random hexagon containing it. From A's point of view, if A is on the left side here, the hexagon is on the right. If A is on the right, the hexagon is on the left. And then B is going to be a random point on the hexagon's edge. So now A's path is zero-dimensional. A just looks like a stationary point. And we can have a hexagon, containing A. A hexagon for which A is either on the left edge of the bottom segment or the right end of the bottom segment. And then B will be a random point on the hexagon's left edge. If the hexagon is all the way to the right, B will be on these two segments. If the hexagon is all the way to the left, B will be on these two segments. And in between, B will just span this region. So A is a fixed point, B is a random point in this region. We want to know the median value of the distance between A and B. Well, first of all, note that B is uniformly distributed across region B. It has an equal chance of being any point in this region. So, if we want the points that are most D away, where again, we're letting D be the answer. If D is the answer, if we want to know that the chance that a point is at most D away from A is exactly 1/2, then if B is any random point in this region, the way we can draw distances between multiple points at once is we can use circles. A circle of radius D centered at A. A circle of radius D centered at A is all points exactly D away from A. Then if you're inside the circle, you're at most D away from A. And if you're outside, you're at least D away from A. So this region right here, since B is a random point in this region, and since B has an equal chance of being at most D away from A and more than D away from A, if we draw a circle at A with radius D, then this circle must bisect this region. It must cut it in half. Okay, so now we've turned this into an area problem. We want to know the radius of the circle such that this region on the inside is exactly half of the total region. Well, the area of the total region is pretty easy to compute. The hexagon had area 1, and this just looks like 2/3 of the entire hexagon. So the area of this region on the inside is 2/3. That's an easy problem to do. The question is, what are we supposed to do about this inner region? It has an extremely bad boundary. It has like 4 segments and then an arc of a circle.
Well, here's the thing. You'll notice that the bottom, right here, the bottom of the region looks an awful lot like this side of the region. In fact, this bottom part would fit very well into this part right here. It looks like a puzzle piece. It looks like this piece is supposed to be used with itself. And so that's what we're going to do. We're going to take this piece and we're going to rotate it. We're going to rotate it 6 times around A to get this picture. Now, the hexagon, this region was cut in half by this arc of the circle. In fact, every one of these regions, by symmetry, is cut in half by the circle. Therefore, this circle cuts the entire union of these regions in half. Now, what is the union? Well, it's a hexagon. What is its area? Well, the side length of this is twice the side length of the original hexagon, right? This is the side length of the original hexagon, and we're just having it twice. Therefore, this hexagon has area 4. Because the original hexagon had area 1, this is twice the side length. The area is 2 squared as much. That's 1, so that's 4. So this whole hexagon has area 4. The circle cuts every region of it in half, and therefore cuts the whole thing in half. So the circle has area 2. So if pi r squared equals 2, we must have that the answer, the radius of this circle, is equal to square root of 2 over pi. If pi r squared is 2, we just divide by pi. R squared is 2 over pi. R squared is 2 over pi. So that's the answer for a hexagon. But we didn't ask about a hexagon. We did ask about a 2022 gon. And 2022 gons are still just as hard to illustrate. So you're not going to get one. You're going to get an 18 gon. But the idea is that this is similar enough to a 2022 gon. The property that they share, well, we'll see. But we're just, for now, pretend we're using 18 gons only for illustration. So if we do this maneuver where we cancel out the top and bottom sides after assuming A is on the bottom, then we can assume B is on the left. We can look at the frame of reference of A, and we get this region. But we run into a pretty big issue. The argument earlier worked because we knew the circle bisected the region because B was uniformly random in this region. The problem here is that for the 2022 gon, B is not uniformly random in this region. You see, every edge, B should have a fair chance of being on every edge of the polygon, right? But look at this region. It's much thicker in the center and much thinner at the top. If I had a uniformly random point in this region, it would have a very unfair chance of being in the center. If I look at the rhombus, the parallelogram up top, devoted to the top edge, that's very flat. It has a much smaller height than the parallelograms in the middle. So uniformly random point in this region is very biased towards the middle. It's very much more likely to be in the bigger parallelograms in the center than it is to be in the thinner parallelograms at the top. And so, since B is supposed to have an equal chance of being in every parallelogram, this doesn't quite pan out. B isn't uniformly distributed across this region. So what are we to do? Well, you'll note that in the center, things are balanced. When it comes to the edges, the center and the edges they don't work together. But the center works with itself. You see, the region here, the parallelogram corresponding to the top middle edge, has the same area as the parallelogram corresponding to the bottom middle edge. That's the neat thing about 2022 ones, because 2022 is of the form 4n plus 2. It's 2 mod 4. That means that while there will be a bottom edge and a top edge, there will not be a left edge or a right edge. There will be 2 left edges and 2 right edges for a 2022 gon. Because, well, if we look at the polygon, we have one edge here, two edges here, two edges here, one edge here. That's 6 edges, plus 4 times some number of edges in between.
And so 4 times some number plus 6 is 2 more 4.
So for the 2022 gun, you can count that there will be 2 left middle edges and 2 right middle edges. And then we can use this to our advantage. Because note that instead of canceling out only the top edge and only the bottom edge, we can cancel out this entire arc. We can cancel out every edge above the middle 2 edges, with every edge below the middle 2 edges. So we can assume that B is on neither of these because they cancel out. And we can assume that B is always on the left side of the polygon. Always in the middle of the polygon. And then, without loss of generality, always on the left 2 edges. And only then do we do the frame of reference thing. And we know that B is now uniformly distributed in this region because the parallelograms have equal areas. And the circle bisects this region. Because if any point has an equal chance of being on either side of the circle, because B is uniformly distributed, it must bisect this region area-wise. Now, the thing is, this region, earlier what we did with it was we treated it as a puzzle piece, and that worked out well. It tiled with itself. The problem is that this piece doesn't look like it fits into itself. And so here's the second magic trick. What we do is note that this puzzle piece would be completed by the region between these dotted lines. We're going to add it to the bottom, and we're going to add it to the top for balance. Okay? We're going to take this region. Because the circle bisects the center, and because the area on the top equals the area on the bottom, the circle also bisects this whole thing. So that maneuver, what we did just there, is we went from this region, where B isn't uniformly distributed. What we did was we noted that B is uniformly distributed in the center, and that's all that matters. The sides are being treated unfairly, right? They are weighted less in this area, but as long as they're being treated unfairly equally, everything is fair. So the circle cuts through this region in exactly half. And so when we use it as a puzzle piece against itself, we note that this whole thing is a 2022 gun with twice the side length of the original. It again has area 4. The circle cuts every one of these bananas in half, so it cuts the whole banana bunch into half as well. And so the circle is area 2. So if the banana bunch is area 4, and the circle is area 2, pi r squared equals 2. So r is again square root of 2 over pi. The answer is neither more nor less, but for the 2022 gon, and for all 4 n plus 2 gons in general, when a polygon is regular and has 2 mod 4 sides, then the median distance is square root of 2 over pi. That's the problem. So, now it's time to turn to questions. That's the end of my talk.
Are there any questions regarding the math? Yes, there is a question. The microphone is not wireless, unfortunately, so you have to speak loud.
Okay, I'm pretty much not an expert, but can we go back to drawing 2?
Okay.
All right.
About where?
And then dividing that by 2, and that can be 0, right? That was.
Yes. Hey, you want me to explain the slide?
Yeah. Why f can't be 2 to infinity?
Well, the problem with that is that 2 to the infinity is not an integer.
Or is that the definition of infinity?
Okay, so f is a function that maps to the integers, right? And so this must take on some integer value. And I want you, and the question is, if this
integer value can be divided by 2 an infinite number, or as many times as you want. What must it be? Well, the puzzle is, try to find an integer that you can divide by 2 many times. You will not succeed unless you choose 0. The reason, okay, there are many ways of looking at this. One is through the prime factorization. If you prime factorize any number, there will only be a finite exponent of 2. And if you divide by 2 a bunch of times, that exponent will eventually be down to 0, and then you can't divide it anymore. That's one way to look at it. Another way to look at it is by size, because we actually use size when we're talking about GCDs in general, not just 2. If we have a number like 1,000,000, and we divide it by 2, it's going to get smaller. It's going to get to 500,000. We divide by 2 again, it's going to keep getting smaller. It's going to get closer and closer to 0. Dividing it by 2, if we divide it by 2 enough times, it'll eventually be so small, it'll not be 0, but it'll be less than 1. It'll be between 0 and 1 in magnitude, right? And the thing is that a number between 0 and 1 is just not an integer. So if we divide by 2 a bunch of times and we get something that isn't an integer, we have a contradiction, because every value of the function is supposed to be an integer.
Sorry, but for mathematics, 2 to the infinity is not integer.
2 to the infinity, well, 2 times 2 times 2 times 2 forever.
Yeah.
You can try to define it, but the way, for our purposes, 2 to the infinity is just not an integer because it's too big to be anything.
Then it's fine.
Raise your hand. Oh. The lady?
How about making a problem?
This problem?
Yeah.
Okay.
How do you make it?
So the way I composed this was because I was just thinking about the median distance between 2 points on, I was thinking about the median distance between 2 points on the square, and the reason was not because I was doing this randomly, but because it was a past AMC question. Okay, so a previous question on the AMCs asked you to find the median distance between 2 points on the square. Actually, I don't think it asked for median. I think it asked for like the chance that the distance is more than a half if the square is area 1. Whatever the question was, the standard way you're supposed to approach square problems is that you like write a variable for one side and write a variable for the other side, and then you draw some graph in the plane. It's called geometric probability. That's the standard approach to it. But I approached that problem differently by like actually shifting the square and looking at the frame of reference. That operation. And so the Elmo problem then was created by wondering, the standard approach to that problem doesn't generalize beyond squares. It actually had to like use the Pythagorean theorem and use the fact that the square had a 90-degree angle. But my approach would generalize. So I wrote this problem just by generalizing that problem to more polygons. And noticing that first of all that you could do it for hexagons by using this little trick. And I actually thought for a while you just couldn't do it for larger polygons until I realized the uniformity thing could be patched up by looking at the center only. So yeah, that's how I wrote that particular problem. Problems in general, there are 2 ways that problem composition is tended to be looked at. One is you write a problem forwards, which just means you write a cool looking statement down and you solve it and you see if it's interesting. It's like gambling on problem statements. And the other way, which is my preferred writing method, is to write problems backwards. You start with the idea for the problem and you build the problem based off of that. For those problems, I can speak to them better. What you do is you start with your idea for a problem, like a really neat thing that you can do in math. And then the idea is you make a problem that forces the contestant to find it. And through playing this game of how do I force the contestant to see it, often you can generate a problem that way.
If there's another video, yes.
Yeah.
I have a quick question, not a math question, but if you get a hexagon, but you don't get a polygon, if there were you got a problem, how many points would you get for the hexagon?
We were wondering if we were going to encounter that question
while grading, it turned out that the new moppers, out of them, almost everyone got 0 points on the prom. No one made any substantial progress, except for one single kid who got a 7. So we actually did not encounter that problem at all. But if someone did get the hexagon, my personal opinion is that they would get a 5, because a 5 generally, out of 7 points, a 5 generally indicates that you got the core idea of the problem, but there's a significant gap that is not too hard to fix. And I do think that that qualifies this description, that there is a significant gap in the solution due to non-uniformity, but that's not too hard to fix. There's also a case to be made for 4, I think. But 4 or 5 would be a reasonable solution.
Back to the lady there. Yeah.
How old were you when you made that?
Right. So I think I did the Ames. I actually don't remember when I did the Ames problem, but I came up with the idea for this in like. I came up with the idea to do it on a knot square, like 5 years ago, I would think, and then I figured out how to turn that into how to do it on a hexagon, like a few months after that, and then how to do it on a larger sided polygon another few months after that. So I think I made the problem in 2019, but a few things. One, 2019 is 3 mod 4. So you still have to wait another 3 years to use it if you want to do a special thing with the year. So that I did. I waited till 2022 to propose a training contest. Also, I do think this was my first time proposing to a contest of the level of Elmo. So I think that 2022 Elmo was just very good timing. Yeah?
Does it have to be 2 mod 4?
2 mod 4? Yeah. I'll get on chocolates for this. I want to draw. How does this work?
You have chalk, actually. There is a movie of chalk down here.
Okay. So.
Maybe we have more chalk.
Okay. Let's play another guessing game. Who thinks the answer for, okay, let's choose an octagon. That's a good number. Who thinks the answer for an octagon? I promise this time it's not a trick question. The answer is actually more or less. So place your bets. Who thinks that the answer for an octagon is more? Less? Okay, we'll see who's right. Yeah. Okay, so let's go back to the step where we looked at the frame of reference of an octagon. We have some point on one of these sides and another point here. So we have a point B on one of these 3 sides and another point A on this side. And let's shift it. Okay, so we have B being in this region. And if we draw a circle with radius square root of 2 over pi, which is our like guess for the answer, right? If we draw a circle with that radius, we're going to see that it actually cuts like this. You'll see that the middle region, it leaves a little corner here, and it leaves stuff over there. Okay, so if B were uniformly random in this region, this would be the answer. Can you guys see this diagram in the back, by the way? Okay, cool. If B were uniformly distributed in the whole region, this would be the answer. But the sides are being weighted unfairly. They need to be weighted extra. Okay? So these sides are thinner than they should be. So we need to, so a point actually has a larger chance of appearing in the sides than they would if it were being chosen uniformly at random. So now let's look at what portion of the sides the top and bottom are receiving. Well, the top half, this region above the circle, is not only getting their portion, not only getting the top region, but getting a little bit extra off the bottom region. And the bottom region doesn't even get their full share of the sides. You see, the sides are more valuable than they appear, and the cut above the circle is getting more of them than they deserve. So this region is being given unfair treatment. B has an actually higher chance of appearing above this cut than it looks like. And so this circle actually needs to have a larger radius to account for that. The circle needs to take some stuff away from the top region because the top region is being too greedy. And so the circle has to have radius larger than square root of 2 over pi. And so for a 4n gon rather than a 4n plus 2 gon, it turns out that the answer will be more than square root of 2 over pi.
I have a question. So what is the median score of the Brazilian coaches for problem 2?
I think 0. I would guess
0, okay. Well, that's the median.
I don't know the score distribution for that, but it's like extremely difficult. It is not reasonable to put on a contest, which is why it was put on a revenge contest. But it's extremely not reasonable to put on this contest. If like someone put this on a contest, it should seriously be questioned if they should be fired, because like the problem solution is really simple, but it is extremely difficult to think of because it is so unintuitive. It is so unintuitive that such an algebra problem would be actually a number theory problem. It does not look like its solution. The problem does not look like it matches the solution it has. And so it's really a lot more challenging than it looks.
Well, if there is any last question, we'll take it and then we have to move on to the monthly contest awards. Any other questions? Yes, Elaine.
Say that again, Robert.
Have you ever come across any problems that you couldn't figure out?
I mean, yes. The question was, have you come across problems you couldn't figure out? And the answer is, yes, this is a good thing. In particular, when I started out doing Colloquium math like early on, I think I basically just stuck to problems that I kind of felt comfortable with. It's not the greatest thing. At some point, I decided to start not actually picking problems myself, because I kept on picking problems that I was drawn to. What I did was I wrote a program that picked random problems from the IMO shortlist, the problems selected for the IMO, and I just worked in them. And the thing is that these problems often looked pretty challenging. They looked way harder than I thought I would be able to do. And so whenever I could actually solve such a problem, I was like extremely pleasantly surprised. I was very happy that I could like do a problem that was way outside of my comfort zone. And so I think it's actually really good to try problems you're not comfortable with. If you fail to solve them, then that's as expected. But if you actually succeed, you get such a confidence boost, and you also get the ability to work on problems that look impossible without giving up. And I do think that that's a very neat skill to have, pushing your comfort zone, whether in math or in life in general.
Let's thank Aspen once again. Our two assistants, Ryan and Aaron, and they want to give something to Aspen.
Yes, Aspen, we have a small gift from us and signed by a lot of people here. So thank you so much for all you've done. Oh, yes.
Very important.
Yes. Okay. So I can read the title. It's called The Millennium Problems, the 7 Greatest Unsolved Mathematical Puzzles of Our Time.
You can open it and check what the kids have done.
Where is this? Oh, I see. Wow. Thank you all.